I've only got 10 minutes before I have to go to finding a job lessons, but I was watching Janet's video on a torus inside a torus, and I remembered when I was in Bolivia, I spent some time trying to think about what other bizarre kinds of topologies that the world could have, which would maybe appear to the people in it like we live on the outside of a sphere, when in fact we were inside something. And because there are a lot of mysteries about rotation in particular. Thinking of Newton's bucket and this business of particles, I think it's gravitinos that have spin 1 1/2, that they spin 3/2. And so I was thinking about Roger Penrose and his diagrams, and I drew a diagram in the style of Roger Penrose. And this, I think, is what Janet was talking about, a torus inside a torus inside a torus. These things are tori. I'm drawing them like that, but in fact, this thing goes kind of down and around, if you see what I mean. These are the cross sections. These toruses are in that plane, the little ones. The medium-sized ones are lying in that plane, and the biggest one lies in that plane. So we've got three planes. Like that. I wonder if I can label them. So there's a torus in here. I'll call that A for the big one, B and B prime for the little ones, C and C prime for the tiny ones. So A, the B toruses lie in this plane, and the C toruses lie in this plane. And I just kind of wonder if there isn't some abstract, if there's some abstract way of thinking about spins, which a picture like this would pick up, in the sense that if you turned this big torus through 180 degrees, you would be performing a switch of the senses of the little tori. So it seems to me like you could come up with some sort of geometric group to describe the invariance of the. It seems there's definitely some sort of group structure in the mappings that you could do. So there must be a lot of models like this which might capture this weird kind of non-local, I call it a non-local hidden variable. It's because it's only the system as a whole that has this particular property. So when you take two disparate parts of it, only when you connect them together with an empirical experiment of some kind that you can perform, do you know what the variable value was, because the variable is a product of the whole thing, not it's not something that's localized property of any part of the space. So like the example of the is the EPR, Einstein-Podolsky-Rosen paradox, where you have a spin up and a spin down photon produced at the same time, traveling in opposite directions, and you perform spin measurements long way away. Then one of the people one person chooses one axis, one direction to measure the spin of the photon in, and the other chooses another. And they get their definite outcomes, but it's only when you bring the two together that you know the value of the hidden variable, which was the spin of the original whole thing before it split into two halves. But maybe I've completely misunderstood the EPR experiment. I don't know what it was that you with a lot of these quantum mechanics problems. You tend to be presented only the middle of the middle part of the argument presents this conundrum, but people ignore what's happening on either end. I mean, if you think about, it's like you have a particle accelerator at one end and a photon detector at the other, which are immensely complicated devices, and you forget about the particle accelerator and the photon detector, and you concentrate entirely on the empty space in between and say, well, look, there's a big conundrum in this, well, what's real in this empty space? But you're ignoring the reality of the generation of these particular particles, photons, electrons, whatever they are, and you're ignoring the way that you detect their presence, and you're ignoring the statistical nature of the whole thing, and then you're presenting this conundrum of some completely abstract thing which is supposed to underlie the physical measurement. But what I'm trying to get at is, in a sense, our models of that intermediate space, and it is a purely mathematical space. It's probability amplitudes. It's not even probabilities that we talk about existing down there. Why can't we have spaces like that in quantum mechanics to these things might actually help explain the phenomena, but then people will say, oh well, the universe isn't toruses inside toruses inside toruses. That's mad. They'll say the universe is locally a flat Euclidean space, and our experiments, our theory, our physical content would evaporate. It would be an entirely intellectual. But I think it's entirely intellectual because you're ignoring the whole system of statistical gathering of data and all of that stuff. So yeah, of course it's abstract and it's an abstract space, but I don't know. There's something about physics that it seems to want to be in two places at once. It wants to talk about the tangible, real world, and it wants to be able to talk about the. And it's just because of extreme reductionism, people saying, well, we've got to explain every phenomenon we observe in terms of things that little dead particles do when they bump into each other. And what's your basis for starting to for picking that as your starting point for what is a physical theory? It's a disaster. It's this extreme reductionism, and for me it just doesn't work. It leads you to an incomprehensible universe, and it's anybody's guess what's going on. In the end, it's the people who guess loudest and hardest and most often that their version of reality is what carries the day somehow. Well, how? But I've got to go and try and find a job now.